Okay, so welcome again, everybody, to the Chameleon user meeting. We're going to talk about Chameleon, what's in the future, looking forward, and what's in the past, over the past 10 years of Chameleon. And we'll start a little bit more with the future because we figured you'd be heading for the exits after 5 minutes of the past. And then we'll have a little bit more of the future at the end also to keep you all here. So first, a quick introduction to the system, Chameleon in numbers. As Deep mentioned, there were multiple phases of Chameleon. The system was first funded in 2014 and became available in July, at the end of July of 2015. So that means that last year, at the end of July, we celebrated our 10th birthday. We had virtual cake. No calories, okay? So it's a 10-year-old system. Why this is significant? NSF doesn't typically fund infrastructure systems beyond 10 years, but for Chameleon it did. And the reason it did is because it became well established in the community and critical to much of the research and education activity in computer science that was going on. And how well established you can see from these numbers. So over the 10 years of the system existence, we had the honor to serve over 14,000 users at this point who worked on many projects in research and education, and at this point produced over 1,000 papers. I'll talk about that a little bit more. We have data going back to 2025, but we of course collected on an ongoing basis. So some basic parameters, the most important thing to know about the system. If you're new to the system, first of all, we support a broad set of experiments, or aspire to support a broad set of experiments. So we have very diverse hardware with many different hardware types, so that investigators or individual investigators can look at how their algorithms change across a range of hardware. We support from very large hardware to small devices. So small devices meaning edge computing systems, Raspberry Pis, systems that you deploy in the field. And we are also a distributed system. So the core sites are at TAC, the Texas Advanced Computing Center, as well as University of Chicago, with the hardware at this time being in the Argonne machine room. And we're of course adding NCAR as a third site to Chameleon, and we'll talk about that more in detail. So broad set of experiments, meaning diverse hardware and as much scale as we can afford, but it's also a system that is deeply reconfigurable. So the idea here is we support computer science experiments that in power efficiency, in performance variability, and those experiments typically need access to performance counters, access to power metrics. So those things you need from bare metal reconfiguration. But we do also support a spectrum of reconfigurability options. Why? Well, sometimes because, for example, for devices at the edge, it's not possible to, they don't support IPMI, so you can't easily reconfigure them on a bare metal level, but also to provide a little bit more of scale. So virtual machines allow us to share resources. Well, you can deploy multiple virtual machines on one resource, so we can share resources more efficiently, and we can implement that scale aspect I was talking about. But sometimes you just need bare metal reconfiguration, and that's when we do that. We innovate in methodology, support facilities for experiment packing, management, and sharing, and support something called practical reproducibility. So using reproducibility as a mainstream method of scientific exploration. And now, to make the system cost-effective but provide avenues for evolution, we also configure the system based on a mainstream core, so based on OpenStack, and then develop capabilities on top. So what hardware do we have? To tell us about that, I would like to invite to the podium Mike Sherman, who's the Chameleon infrastructure lead and also point of contact for the University of Chicago site, and Cody Hammock, who is the point of contact for the site at TAC. So they will tell us about what we support on those sites.
Sure, yeah, hi. Hi, everyone. I run the Chi at TAC and KVM at TAC sites. They are probably the biggest site, I can say, with confidence. They have the widest range of hardware. There's easily 6 different CPU architectures, a couple of different InfiniBand interconnect generations. We've got 2 petabytes of flash storage in the shared storage cluster that services both main sites, and sort of a handful of GPU variety, both from NVIDIA and from AMD.
Okay, I'm Mike Sherman. I'm the infrastructure lead for Chameleon, and so I'm in some sense responsible for all the hardware working correctly, but I'm also the site lead for the Chiat UC site and our edge hardware, Chiat Edge site. Like Chiat TAC, Chiat UC has about 130 bare metal nodes, about half the size of TAC, but still has a wide range of bare metal nodes with fast NVMe storage drives, InfiniBand, and we've got a set of nodes with NVIDIA A100s in there. And then Chiat Edge is our edge computing test bed, which lets you, instead of launching VMs or bare metal servers, lets you run containers on, as Kate mentioned, Raspberry Pi class edge devices. And importantly, they don't have to be in a data center, they can be anywhere. And you can take your own edge devices and enroll them in Chiat Edge without asking us. You bring your own device with your own user and attach peripherals and sensors and cameras and use this to run experiments where you gather data, actuate things, do edge to cloud experiments, and generally get the edge into our cloud.
Thanks, guys. I would like everybody to remember their faces, talk to them about hardware on those respective sites. But in this diagram, you see Chiat UC, which is University of Chicago, Chiat TAC, and then there is nothing in that box for Chiat NCAR, and that's because this is a site that's coming online today. And here to tell us about the site and about NCAR are Janet and Bodhi, who will tell us how the site was built, what it offers, and what its future is. Bodhi?
Alrighty, well, thank you. My name is Bodhi. I'm a undergrad here at CU Boulder. And along with Jeanette, I'm one of the site operators for NCAR's Chameleon site. And I'll let her introduce herself.
Oh, yes, hi, I'm Jeanette Tillotson. I'm a senior HPC systems engineer here at NCAR.
All right, and welcome to NCAR. We're the National Center for Atmospheric Research. We're managed by UCAR, which is the University Corporation for Atmospheric Research and is a consortium of universities with shared atmospheric research interests. The building we're in right now is the Mesa Lab, which was the original building constructed back in the 60s. But we have a whole lot of other facilities. We have the Mauna Loa Solar Observatory. We have the Research Aviation Facility, where we have a couple planes. That's our C-130, which we can fly through some extreme weather. But generally, our exports as NCAR are some weather and climate modeling. We have CESM, which is our community or systems model that couples a lot of smaller models for land and river, ocean, all of that kind of stuff. We have the WRF model, which is our weather research and forecasting model. And then we also have MPAS, which was recently adopted by NOAA for the National Weather Service forecasting, which is pretty cool. But all of this is possible because of the Computational and Information Systems Lab here at NCAR, which runs our supercomputers up at the NCAR Wyoming Supercomputing Center. And I will let Jeanette tell you a bit about that.
All right, so I stole this slide from another presentation, but it's a nice slide just showing what our resources are at NCAR. We have, of course, our flagship machine, Cheyenne, came offline in 2023 and was replaced by Derecho. It's a Cray HPE machine with 2,570 nodes, about 82 GPUs in there, all A100s. We also have a Casper system, which is a Viz system. So we buy one-off machines, we put them in that cluster, use that for visualization, high throughput computing, things that our flagship machine wasn't designed to do. We also have several storage systems. We've got a large Glade or campaign store that's mostly where the users store their data. We also have a scratch storage system, which is luster-based. We have an object store and tape library. So those are the main resources that we have here at NCAR. Next slide. Yes, so our data center is quite unique. It's a world-class data center. 153,000 square feet, 24,000 square feet of raised floor. Our raised floor is awesome. It's a 10-foot raised floor. Having worked in data centers that are 2 and 3 foot raised floors, I can tell you having a 10-foot raised floor is really lovely. And that's useful too. We actually use that raised floor for part of our cooling. So I'll talk about that in a minute. We do collaborate with the University of Wyoming. They share that data center with us, and they get part of Cheyenne, or sorry, excuse me, part of Derecho, as I used the wrong term. They get part of Derecho to do computing, so we have a contract with Wyoming and they use some of our services for their university. The building is LEED Gold certified, which is just an energy efficiency. I put a link there if when the slides are made available, you can check it out. That data center has a PUE of 1.09. What does that mean? It means for every 1 watt that goes to the supercomputer to power it or to the storage system to power it, 9/100ths of a watt will be used for the rest of everything else. That's cooling, that's the lights in the building, that's the system for getting into the building, all of that. So it's very efficient. Almost all of our power is going to run the supercomputer, and that's the key for the building. And it's mostly power or cooling that we're concerned with, right? That's usually what's used besides the power for the machine. An average PUE is like 1.5. So, so a half a watt goes for cooling and all those other things for every watt. Some data centers are 2, PUEs of 2, which is crazy to think about. But our data center is 1.09, and that's pretty good. I don't know, there's not many data centers that are better than our data center. We currently have 4 megawatts, but it's upgradable to 32 megawatts if we need to. And I have a little, there's a little 360 thing you can go and check out our data center. I put a QR code up there in the corner if you want to grab it, or there's a little bit.ly link here if you want to go. And I'm just going to show a few slides from that. So here is when you walk into our data center, or you walk in, there's a little museum. And at the end of the museum is this right here, this window. And you're looking into one of our pods in our data center. And this is our air-cool pod. You can see in the ceiling there's holes. And so what happens is the hot air will just rise naturally up into the ceiling. In the ceiling, it will just cool off on its own. When it does, there's actually a space. There's 2 sets of windows. There's one here and there's another. And you can see this look down. Those are actually in between those 2 windows. And that air will naturally fall down into this cavity. And then there's filters down here, as you see. That's our raised floor underneath. And then there are fans that will pull the air back into under the floor and then let it go back up. And there are chilling pipes in between those filters and the fans that will chill it if it needs to be chilled. But often we do all evaporative chilling, which is nice. And we don't run our chillers. We do have big, huge chillers, but we rarely turn them on, which is lovely. We just let the natural evaporative cooling do the work. And that's why we get such a low, such a good PUE value. Next slide. So this is just from the video. The little 360, there's a little video here of this. You can see the fan wall back here. This is the fan wall that's underneath the floor that's pulling the air from that filtered side into the floor. And then this is just a little picture there. It shows the fan wall. That's this red thing right here. There's our data center. This over here is that space I just talked about where the air comes down, goes through those fans, and then gets diverted back up into the data center. And then this is our chiller. I just like to show it. Our heat exchanger, as I say, it's our heat exchanger. It's massive. I mean, that's 10 feet tall, right? So we have a huge heat exchanger down under the floor. Of course, the water, chilled water comes in, and the hot water comes in this way, and then they change their heat and then go back their separate ways. There's arrows which are hard to see. These arrows on this side are coming up this way. The arrows on this side are going down that way. So this is the chilled water going back into our machines, and then this is the hot water going back out to get cooled. So, and then again, this is also, we do direct-to-chip cooling, so that's what most of this is used for, right? That direct-to-chip cooling. The air cooling is done differently, right? So, all right. All right, and then I'll turn it back over to Bodhi.
Well, cool. Now I get to talk about our new hardware. We have a little time lapse going of Jeanette and I doing the layer 1 networking for this cluster. But we started as a volunteer site in January of 2022. But as Kate said, as of phase 4, we're being upgraded to a full site. And so we have a bunch of new hardware that's in production, and it seems like we'll be able to document and release it to users this week, which is very exciting. But we have 40 new general compute CPU nodes that all have 16-core AMD processors, 64 gigs of RAM, 960 gigs of NVMe storage, and 2 25 dual-port links. And then we have a Ceph cluster of 5 Ceph nodes, which gives us about 225 terabytes of distributed storage. And those have dual 100-gig links. And then we still to come have 15 GPU nodes. We had wanted to get those by about now, but between the time that we quoted them and we're going to order them, they had doubled in price. And so I think our plan as of now is to kind of wait out the supply chain, and hopefully those will be coming back down in about 6 months. But ideally we have some more workstation type GPUs like the RTX 6000s, and those will have good RAM, good storage, and yeah. These are some pictures of our new hardware. We have some cool clusters. And then a couple other things. We have multi-tenancy networking and a connection to the Fabric testbed coming. And then we would like to re-add our Thunder nodes as well. And that's all we got.
Fantastic. Thank you both. Everybody now knows we have a site at NCAR. Please don't overlook it when you make your reservation on. This microphone should still work. All right, so again, for those of you who don't know, just to go over the experimental cycle on Chameleon, you of course start with whatever hypothesis you have. You discover resources that we have on Chameleon for your experimentation to prove or disprove that hypothesis. We provide very fine-grained information about those resources. We support non-fungible resource models. So in other words, if you're doing experiments with, let's say, performance variability or power management and want to have a consistent resource baseline, you can reserve always the exact node that you're working on. We've got availability calendar. And then once you discover which resources you want, you can allocate them. We support advanced reservations, so you can make an advanced reservation even for GPUs. They're going to be there for you. The leases are bounded, so there's a defined start time, defined end time. And then, like I said earlier, we support bare metal containers. We provide some images already configured for you, but you can configure them some more and snapshot them. And we support orchestration via Terraform or Python. And now to tell me what's wrong with the picture, I would like to invite Paul Marshall, who spearheads our efforts in AI, and Mark Powers, who's the DevOps lead of Chameleon. So take it away, what's wrong with this picture?
All right, thank you. One major problem that we've identified is obviously with the resource discovery process. So when you go to Chameleon to find resources, we have, if you know, the hardware browser where you can find kind of all of our hardware, at least for the bare metal sites, in one place. And that's great, but the problem is you can't find out when it's available. So you get into this loop of like, you find the hardware, you have to go to that site, you have to then look for the availability, realize, oh, it's already booked. And then you go back to the hardware browser to find other hardware, go back to maybe a different site, try to find what's available there. So that's kind of, it's a cumbersome process. Additionally, once you've reserved everything, you can't tell what's reserved at every site, right? So you've got to go to all the individual sites to be like, oh, what did I reserve here? What do I have here? You can't see it in one place. So again, you've all this kind of friction in the process, which we have. Yeah. here.
And as Chameleon is growing, we have NCAR, we have edge devices, we now have leases on our KVM site. It's getting very difficult to tell what experiment resources have you allocated to your project at any given moment.
So let's go to the solutions.
Yep. So what we want to provide is a better experience for finding both the hardware and is it available, and bring those together in one place. So we're revamping the resource discovery to bring those together. So when you go to the hardware browser, you'll be able to see the hardware and also right there with it, whether or not it's available, and improve kind of the intelligent aspects of being able to ask things like, you know, adding in AI, things like find me these resources that are available now or available next week. And then it'll pull those up. You'll be able to still reserve them using all the ways, you know, that you're used to.
And then also we're looking to improve how you can manage your leases. So to start, we're planning on having a single source of information for everything you've reserved. So rather than going to every site. So it'll, you know, here's a mock-up where you can see all your leases across various sites and when they're going to expire and what resources those are for.
Okay, thanks guys. Please talk to them. So like they said, those are capabilities that we're planning to introduce in the next 6 months. And they also form a foundation for ultimately building a more interactive AI-based interface to the testbed. And here's just a quick graphic. I won't talk about the research projects that our users did on Chameleon because we want to hear from you in the rest of the day. But this is just a quick graphic of various pictures that I collected of different people presenting on their research and education projects. So we're going to go a little bit into the break with this presentation, I'm afraid, because it's hard to manage everything with so many people coming to the podium, but hopefully it will be interesting. So how does the system grow in terms of users? So we're switching a little bit into this looking back section. So if you were ever wondering how many users use Chameleon and how quickly does that grow, you've got a graph that shows the growth of our user community per year and just showing explicitly new users per year. So what you see from that graph is that we were, you know, ramping up slowly, came to, on average, adding about 1,000 new users a year. And then in the last couple years or so, the growth of the system really exploded in terms of community buildup. So in the last 2 years, we added 2,000 users each. And this is mirrored by the growth in terms of projects, right? So on the second graph here, you see how many new projects we added per year. And you also see that it was growing and then it continued to grow to over 250 projects per year. How many of those users use Chameleon on a regular basis, on a monthly basis? So you've got a couple of graphs here. One is the users who log into Chameleon. So to log into our portal, and for that, we only have data going back to 2023. But we have data going back much further for the users who actually use Chameleon resources. So in other words, who use OpenStack to either allocate resources or reconfigure them. And the interesting thing that you see from the second graph is that if we go further back, if we go several years back, we would have around 200 users on average, let's say, logging into Chameleon using Chameleon resources, but that number, again, in the last 2 years, really rose very significantly. And you also see a difference in the monthly number of active users between the first graph and the second graph. And I won't go into the detail for how this happens now. We've got actually a PERC paper this year analyzing the usage of Chameleon, and we summarize the findings there. You can also talk to me about this. Another interesting thing that you see in these graphs is the academic year reflected in the usage, right? So you see very high usage during the spring and fall semesters, and then it drops off during the summer and winter holidays. So really, we set our clocks by this. It's very, very regular. Another interesting question is how many PIs there are in the system and how many stay with the system. So we sort of mapped the second graph shows you what proportion of PI is active for a given number of months. And the interesting thing that you see here is that both for overall number of PIs and the PIs in education, a substantial percentage of the PIs, 20% roughly, for educational PIs are active on the system for 5 years. So they keep coming back to the system every year for a very long time. There is a substantial drop-off after 6 months. So some PIs, 6 months is the limit of your first allocation on Chameleon. So many people just fit within that allocation, and then many of them just keep coming back. The question is, where are our users from, right? And if we just look at this data by the number of users, what bubbles up to the top is the educational institutions. So institutions that use Chameleon for education hold large classes. So in order to get a better idea of how many people might be using Chameleon for research, we asked, where do our PIs come from? And for PIs for all time, you still see the operating institutions on top. So UT Austin, University of Chicago, Argonne National Lab in the top 5, because they had a head start with the users from those institutions, the word spreading there first. But you see also many other institutions, University of Colorado Boulder in top 10, certainly, and many other institutions across the nation in the top 20. So what do users work on? So here's some data on how users classify the project. So I take this data a little bit with a grain of salt, because sometimes users classify things based on what they perceive as their area of research rather than necessarily what the project is doing. So we had a project that was using AI for power efficiency, and I asked, did they classify it as power efficiency or did they classify it as AI? And the answer was operating systems. Okay, so it's like I said, with a grain of salt here. And then institutions across the world using Chameleon. And of course, US is the main place using Chameleon, but it's used all over the world, largely as part of reproducibility initiatives at various conferences where we make Chameleon available to all PIs. How well can we support Chameleon growth? So in other words, a quick look at the usage of Chameleon. So in the top graph you see usage, in the bottom graph you see utilization. Interesting thing here is to note that at the UChicago site and at KVM, utilization touches the 100%. So in other words, and 100% is very, very difficult to achieve on a cloud because resources are scheduled based on when the PI is ready or the investigator is ready, not when the resource is available, right? So, and especially for diverse resources, you may have fewer people interested in that. We still need to support that resource because otherwise research using that resource would not be possible. In the usage graph, you see resource additions for Chameleon phase 3, resource additions for when we added the H100s. Here you see utilization for KVM, and I won't go into the details because we're already cutting into the break, but there is an interesting story to tell about how our usage changed because we introduced advanced reservations for virtual machines as well as bare metal. So the short story is that using advanced reservation bounded leases for virtual machines allows us to control the usage on that resource much better, as well as for the users, right? So again, annotations on the graph and a quick temperature map for which resources, this is a popularity contest really, right? Which resources are the most popular? You can see, of course, GPUs are the most popular, but other resources providing different diversity options are used too. And why do we do all of this? And we do all of this, of course, to support our users' research and education. And Frida asked a very good question about how do we measure support of education earlier on. Actually, many of our educational users are asking that. You're not the only one. what is the accepted measure. And as Deep pointed out, that's mainly students enrolled in classes. But here is how we measure research. So first of all, there are many challenges there. One is, how do we know that this paper used Chameleon, so attribution, and we don't really know unless you acknowledge Chameleon explicitly in the paper. Secondly, how do we find out that the paper is out there? How do we find this paper? We don't know, right? Unless you tell us, really, we don't know. How do we tell papers apart, right? So some papers in some conferences, for example, have many synonyms, right? The supercomputing conference, SC, the ACM conference on supercomputing, networking, and storage, right? So how do we manage to make sure that we identify all of them and which ones to include? So for attribution methods, citation of Chameleon papers is best because it solves the problem both of attribution identification, because then we can look at Google Scholar or Scopus or those other various aggregators and find your paper. Otherwise, you really have to tell us about it. Written acknowledgement in the text is very good because the paper is self-contained as to attribution. But if your student wrote the paper and they forgot to put Chameleon in acknowledgement or in the text or cite the Chameleon testbed, we also will accept an explicit attestation. But this is not somebody telling us that they used Chameleon when they need us to renew their project. This is a website where you have to click a special attestation button and make sure that you consciously make that choice and it's that you really used Chameleon in your research. So how many publications do we have? Till the end of 2025, we've had 982 publications. At this point, we have over 1,000 publications that we know of. This is a lower bound, and like I said, a strong lower bound because we really want to make sure that the publications we count in this number were actually produced using Chameleon. How do we find them? Well, most of them we do find by citation, so thank you all for citing Chameleon. Helps with both attribution and identification. Of the other ones, half of them roughly by acknowledgement and half of them roughly by user attestation. What does it look like through the years? So how many publications in different years of the system operations did we find? And what were those publications? Where do our users publish? So you've got sort of historical data on how many publications were published using Chameleon. On the bottom there, on the bottom of the bar, you've got journal publication, conference publications, thesis and dissertations, and then the purple thing on top are preprints. So in other words, working papers that were not yet published. And when you look at this, the purple grows smaller as you go back in time. This is because those papers are eventually published and they turn into something that is blue or orange in this graph, right? So in other words, if I showed you data for 2025 next year, that purple column would be smaller. Publication by venues, we sort of asked for the most cited publications on Chameleon, where were they published? We're interested to see that there isn't any like specific venues where most people publish. So it's ACM conferences, IEEE conferences, USENIC conferences, journals, conferences. So sort of looking at the most cited publications, it's spread all over the place. So it's not confined to one community, but many different communities. And lastly, just a few words about how AI can help us. We were going to do a demo of chatbot interface to Chameleon documentation. We won't do that because of time constraints. We're already a little bit over. But Mark Richardson, who you saw in the introduction here, was going to show that demo and is working on that project. It's again something that we're trying to release in the next 6 months. If you want to see the demo, talk to him. It would be lovely if you could see it and provide feedback right away. So that will be our small foray in using AI to make Chameleon work and work better for you. But the other idea, of course, is wouldn't it be nice to have a chatbot interface to all of the testbed capabilities, right? You know, when is the next A100 node available on, or, you know, where can I make a reservation on these 3 nodes simultaneously, or in, you know, just sort of talk to the chatbot and have it set up the environment for you. This is very important for both structuring new experiments, but it's particularly important for reproducing experiments. So last Chameleon user meeting was devoted to the question of reproducibility. And one of the recommendations, one of the insights from that meeting was that actually setting up the computational environment correctly, the experiment environment correctly, is the hardest part of the experiment, right? Because you have to get all the versions of all the libraries right very often, all the environment variables and things like that. So the idea is that either user says, you know, set me up this environment, or the chatbot reads from the paper. In the paper, you say, you know, I used GPUs and so forth. And then read the requirement, understand them, reserve Chameleon resources for that experiment, boot the instance, attach floating IPs, do all the tedious stuff that you do with the configuration, and then very importantly, run validation tests, because AI doesn't always get it right. And if you have to debug a wrong environment set up by the AI, that's more time and more frustration than actually doing it from the beginning yourself. So you see a little terminal with code and things like that. We actually have a pilot project going on in that space that sets up the environment and generates tests. We don't have a date for when we're going to provide that interface yet. It's not all that easy to do if those environments are going to be set up correctly, but we're working on it. And how do we train those environments? So as some of you know, at least we have a system in Chameleon called Trovi, where you can find packaged experiments or packaged educational artifacts. There's a quick graph about how this Trovi collection was growing and some statistics on how it's being used. And it also turns out that many reproducibility initiatives, they produce collections of packaged experiments that were packaged with a lot of effort and then reproduced by reviewers with a lot of effort, but then they just leave them there. Nobody really uses those experiments. So we thought maybe we can put them in one place. If we make them available and findable, they will be easier for people to find and reproduce, but they will also become part of the Trovi collection and one way to let the AI know for what an experiments look like, what to train on. And lastly, how do we evaluate those environments and how do we evaluate the AI system for creating them? So here, so they sort of all based on the quote from David Patterson, for better or worse, benchmarks shape a field. It's actually a title of an editorial he wrote at some point. And the better part there is that a benchmark provides a focused way of problem characterization and a very actionable way of evaluating how good an algorithm is or how good an approach is. And there's also a sinister side to benchmarks, like, so things could go off the road a little bit. We're working with a colleague at University of Chicago who is a co-author of something called Software Environment Benchmark, SWE-Bench, which solves a similar evaluation problem to the one that we need to solve, right? So one idea for AI is, can some clever AI take a bunch of GitHub issues and resolve them correctly, right? So this benchmark is GitHub issues that evaluate Claude code, that evaluate AI that codes based on those things, right? And this is their leaderboard here, unsurprising from a few days ago with unsurprising results. So really the Trovi collection is another form of such benchmark that evaluates how well an environment has been configured on Chameleon. Okay, and lastly, parting thoughts. Thank you very much for your patience. The system is obviously growing. We're welcoming more users every year, but we're also now welcoming a new site at NCAR to provide for those users, to provide for that system growth. But the system is not just growing, it's also evolving. And there's a big difference between those two. So Chameleon is an experimental testbed for computer science research, and we have to adapt to the new research problems that it generates. So we need new hardware, new capabilities, and so forth. And also a new approach to interacting with the system, leveraging AI, for example. And lastly, Chameleon implements what I call a discovery blueprint. So in other words, it's not just another system that we really know how to operate. It's a system that is different, but it also continues to be different, to differ from itself, right? It continues to evolve. And therefore, it has to be a collaboration with users, right? So we were always relying on you to formulate requirements, to push on us, to challenge us, to change the system for whatever research needs emerge. And so we look forward to understanding more about your research needs and educational needs in this meeting. So thank you very much. If there are any questions, I don't really want to stand between you and the break. If there are one or two, maybe we can field them now. Otherwise, I will be available for the rest of the day. You can ask me anytime. Questions? Yes? One question? No? Just thumbs up? Yes? Very good. Yeah. Okay.